Now it gives me much pleasure to introduce Greg to you. Greg's an energy and engineering leader helping Australia navigate the shift to a secure and affordable energy future. He's a trusted advisor, translating technical, regulatory, and commercial uncertainty into clear strategy and practical action. He's the founder of Hannergrid Consultancy, which is an energy and engineering advisory service. He has an electrical engineering degree with first-class honours, and he also has degrees in management and public policy. He is an alumni of the Oxford Said Business School and a graduate of the Australian Institute of Company Directors. He has held former senior GM level roles at City Power, Powercor, United Energy, and AusNet. So it gives me much pleasure in welcoming Greg to the microphone and the screen. Welcome, Greg.
Well, thanks very much, Chris, and thanks firstly to yourself, Kelvin and Colin, for organising the seminar program. It's a labour of love, I can see, and I was delighted to be invited to speak to the group in July. So I'll get to my slide shortly, but Chris has given a good introduction there. And so my background is I studied engineering at Monash University in Victoria many years ago now, and always sort of had an interest in the power system and the technical as well as the public policy dimension of that industry, and I've worked in it ever since. And one of the things, and this is probably relevant for people starting out today or new to the industry, is that I've sort of worked in generation, retail, networks, consulting, government and clients, and advising governments and clients now, and it just kind of highlights that it's a great industry in the energy sector, but engineering as well in general. And it's always changing. There's always something going on. It's never static. And for those particularly new to the sector or looking to get into it, particularly still at university or graduates, don't be afraid of change. It's inevitable, and generally some of the most best experiences in your career come during periods of change. So let me start sharing my screen, and we'll get into the presentation. As Chris said, if you've got, we'll run through the presentation, and there'll be time for questions at the end. So is that coming through on the full screen? Just can someone confirm, or is that?
Yeah, just press the slideshow button. Yeah, that's right. Perfect.
Perfect. Right. Yep. So today, basically the topic I was asked to talk about was performance and reliability of the evolving electricity network in Australia, which is a very big topic. But I wanted to kind of give I wanted to give my kind of take on this topic, and I'm quite passionate about the distributed sector as well, and I'll talk about that. But the grid and the energy system is becoming much more distributed than it ever was before. It's a fascinating industry. So I hope I can share my insights, and look forward to the discussion. So basically want to touch on these three topics, really around how the mechanics of the grid, but what's happening, the transition. As I mentioned, I'm quite passionate about the distributed sector, so I want to talk about this new role of the distribution system operator, which is a new and emerging role as we speak. Some of the key things for managing the grid, which is voltage and frequency, and firming the grid and storage, which are critical to the way it's evolving, and then thinking ahead, what does it look like for the future. So this is just a little bit about me, but Chris has run through this. But like I set up my own independent consulting practice late last year, and have had a lot of expertise working in networks, particularly since 2015, but more broadly in the energy sector for over 20 years. So that's who I am. Hannergrid Consulting is Australian business based in Melbourne, registered in Sydney, and down the track, if you ever want to contact me, you've got my details there, and happy to talk further around the industry. So let's start with the grid in transition. It's quite funny because when I started my career over 20 years ago, electricity was a little bit more boring than it is, not quite as mainstream. but remains just as complex as ever. A few more experts around the place these days, particularly in the media, and it's quite funny, but there has been a lot of change. And one of the biggest things that I sort of reflect on is when I started my career, I was working for what was then called NEMCO, which is now the Australian Energy Market Operator, so the power system operator and market. And I used to help run sessions where it was called Introduction to the NEM, which probably still run today. And it would be people new to the industry talk about the fundamentals of the power system and how it all works. And one of the key first slides was, well, you can't store the energy, right? But of course, the energy was stored. It was stored in coal and other fossil fuels. You couldn't store the electricity per se, whereas these days, the energy is now stored in the weather, effectively, solar and wind and really the sun. But of course, you can actually store the electricity in batteries and hydro systems and things like that. So it's fascinating how things have changed, and I want to touch on that as we go. So the grid, electricity grid, and actually maybe before I get into the guts of it, yeah, I don't know if it's possible, Chris. I'm sure it is, but yeah, wouldn't mind just if you want to put in the chat, what part of the industry you come from. That'd be really helpful. I imagine a lot of people aren't from the energy industry, but just feel free to kind of put in
Where
the
is it,
chat.
Greg?
Sorry, you still got me, Chris?
Yeah, I got you disappeared for a minute, but yep, you were about to ask me something.
Oh no, I was just saying. I assume it's possible for people to put in the chat, like just a little comment about which part of the engineering system or industry they come from, if that's okay.
Yeah, that'd be good. Yeah,
Is that
no
possible?
problem. Everybody just type away in the chat.
Yeah, because I realise that while my expertise or my background's in energy, that may not be everyone. So feel free to do that. Hopefully I can see that as they come through. But anyway, I'll get stuck into it. So yeah, the grid basically is evolving. There's a massive transition towards inverter-based resources, and I say inverter-based resources, but effectively they're renewable resources as well. So what we've had is legacy plant, which historically has been coal and gas, but coal predominantly in Australia, has progressively retired and is retiring really over the last 5-10 years and going forward over the same time frame, and is being replaced by wind and solar and other forms of renewables. And even the large-scale wind and solar projects are much smaller and more in number than the legacy coal plants. So you're moving from a system that had dozens of maybe power systems to hundreds, if not thousands, and now millions of smaller power systems across the country and on homes and businesses, particularly in the form of rooftop solar. And the footprint, I guess, or the location of the new generation is much, much more distributed. So creates a whole series of new challenges, but basically, what this chart shows is that, we really are verging on a renewable dominated system at times. I mean, it's interesting. Some of these metrics get used a lot to kind of highlight the progress of renewables. In terms of energy, we still, rely on fossil fuels, but in terms of the new generation that's being added, it's almost exclusively renewable, and it's almost exclusively inverter based, and that's also applying for loads as well, like data centers. And the reason I mention that is that the old system was analog, well, not analog, but it was it was analog, but it was made up of traditional heavy plant, rotating plant, and there were inherent advantages and disadvantages with that equipment. All of the new generation is being connected through power electronic devices called inverters, and that creates new opportunities and challenges for the grid. So I guess that's where we are today, and AEMO has to manage all of this, keep the lights on, and if there's any disruption to that, that they sort of take the blame, which is often unfair. They've got a difficult job, but so what we're seeing is huge amounts of generation in the form of power stations that will relied on coal, like Hazelwood Power Station is one of the most famous ones that's been decommissioned, no longer operating. Let's talk about Eraring, Lawn and forecasts for their closure that are sort of baked into various documents that are prominent in the industry. And what we're seeing is a huge amount of battery capacity being added in the NEM. So based on the one of the most recent AEMO reports, we've had 4 gigawatts of capacity added by the end of Q1 2026, which is quite significant. I think that doubled the total capacity, and the forecast that is needed is 4 times that. So huge amounts of battery capacity needed. And I guess the closure of legacy plant will continue, and we're also seeing strong demand growth driven by electrification, population growth, and new loads, in particular data centers. So the need for generation is always there, but as we're seeing, very strongly dominated by inverter-based resources. So again, the reason why I say that is when you had the old power systems that effectively were a large lump of metal that rotated and used water and steam to kind of get that rotation, it had inherent inertia, which supported the system. It had high levels of fault current, which is important for protecting the system during, if there's a fault, makes it easy for protection systems to see and isolate a fault. Reactive power support came as well from those generators, and they were eminently predictable and dispatchable, and you could manage the grid in real time and instantaneously match supply and demand. And even when, for example, there was a fault on the transmission network, you'd see the inertia of the spinning machines could play a role to support the grid instantaneously, and over a very short period of time, as other control systems would kick in to recover the system. And so with the new inverter-based resources, you don't have the same set of physical dynamics. And so it's just different, I guess. It's not really better or worse, but it's certainly different. And it just means that in terms of managing the grid, it's new. I guess in some ways it's more challenging, but 100 years ago, we built a grid that we sort of have relied on for a long time. That was pretty complex and sophisticated, and we're doing that again, just with a different set of technologies. And one analogy I heard someone share with me recently was that the old sort of power system model was designed to mimic nature, in the sense that rain fell from the sky and flowed downwards in one direction. And that's sort of how the electricity system worked. You had generation going from source to load, and that was it. Whereas now it's more like a tidal system, where you've got two-way flows across the system, where you've got obviously generation that supplies the load, but then right where the load is, particularly at homes and businesses, you've got generation on roofs that can also export back into the system. And as the sun moves up and down in the sky during the day, you get that tidal effect. And so the system is becoming much more dynamic and much more two-way. It's basically a weather-driven system, and all of the new resources that are connected are being connected by sophisticated power electronic equipment that has its own unique qualities. And what that means is, in terms of managing a grid, in terms of power system dynamics, like frequency, voltage, how stable the system is, it's different. And so everyone's playing a role to adapt. And so one of the things that I'm quite interested in and have spent some time working on is the integration of distributed resources, particularly into distribution networks. Distribution networks are the street level infrastructure that supply your home and business. And typically, it's just basically a one-way flow of energy to support the load you needed. And it was typically driven by summer peaks for residential and in sort of business hours for commercial. But now with solar increasingly being added to people's roofs at a suburb and at an industrial level, it's very much become a source of generation as well as a supply of the load. So what that is leading to is the need for a new actor in the system, and this is an actor that I quite like, because it sort of takes me back to my original starting point in the industry at the market operator, where you effectively now need similar functions to mimic what AEMO does at a sort of whole of system level, at the transmission level, at a local level. So this role is emerging, and it's really emerging as we speak, called the distribution system operator. I just wanted to quickly talk about that. And so the reason you need this new actor is basically you've got all this solar and batteries being connected. So, really popular with customers and the population. So over a decade, we've seen, nearly 4 million systems go in. It's approaching, one in three, I guess. It's more in certain areas in new suburbs in Victoria where I am. It's probably, much greater than 50% of the homes would have solar. But across the board, it's it continues to rise. So 1 in 3 on average. In some places it might be 1 in 2. In some places it might be 1 in 4. But nevertheless, that figure continues to grow. And then at the same time, and this has been pretty rapid, we've seen the Cheaper Home Batteries program, which the federal government is running, put in 450,000 batteries, which is the latest figure that's publicly reported that I've seen. And that's really happened in little over 12 months. So it's really only in its second year, just sort of turned one, and you nearly had 500,000 systems go in. So that's phenomenal. And then projections for EVs have always been a little bit speculative, but definitely there's going to be more EVs in the system. And with all the changes and geopolitical shifts that we're seeing that volume rise and is likely to continue to increase to significant levels, well above where they are today. And so what all of these devices are active. They are all connected by an inverter. They all contribute something to the system. But in an unmanaged situation, they can also create challenges, as well as obviously providing huge amounts of benefits for customers and the grid. And there's a need, obviously, to manage the total and keep the system secure. And so basically, when the layperson turns on the lights or their air conditioner or washing machine during the day, everything works and they don't really notice anything, and that's how it should be. And just that bottom right-hand chart, you can see that those yellow and green bars just show how much of these resources are coming into the system. And the yellow bars, solar, including rooftop solar, and it just significant amounts, right? And well in excess of the overall demand. And so that's creating opportunities to store that energy and to use it as well back into the system. So the distribution system operator needs to factor in a whole range of things, but I've just put a definition there. Basically, it's the entity responsible for operating and managing the distribution network in a safe, reliable, and efficient manner, enabling the integration of distributed energy resources and facilitating competitive energy service for consumers. So all of these resources, as I said, are active. They need to be, managed in the sense that they don't do any harm. But on the flip side of that is that they've got the potential to create lots of benefit as well. And if left unmanaged, that benefit may not be realised. And of course, with customers and investing in their own systems, it makes sense that you want to maximise the use of that energy for the broader benefit of the system. So there's some of the fundamentals of what's needed for a DSO. And when you compare it to other parts of the system, at the moment on the left, what I call the TSO, that's a sort of transition system operator. That's what AEMO is in the NEM, and in the WEM, they basically manage the grid at the transmission level. So basically in Victoria, like transmission really starts at 66 kV, but anything really over above 66 or 132 is transmission, all the way up to 500 kV in Australia, and they operate the wholesale energy market, the bidding to dispatch, managing system security, frequency control, long-term system planning, and all of those bulk supply points are managed through AEMO in conjunction with the market and particularly the TNSP, so your AusNets, TransGrids, Powerlinks, those networks. The DSO is effectively a new role that's been determined that the DNSPs, which are the distributors, will manage. They've got to manage the LV network in their own patch, coordinate the DER, distributed energy resources, also referred to as CER, customer energy resources. And they've also got an opportunity to procure network support services and other services from those distributed resources, manage local congestion and voltage, and interface back into the TSO. So one of the key distinctions is that in the past, it was almost like a blanket universal operator that AEMO did everything on behalf of the total system, and it was effectively a state-based arrangement, if not a nationwide arrangement. But as you have more distributed generation, the local impacts matter. all the way down to local voltage profiles within a suburb or a postcode. And the DNSPs are playing a role to kind of really focus in on that level of granularity. And it still leaves the DNSPs with their traditional asset ownership role, where they receive a regulated rate of return, connect customers, and keep the network safe and maintain it. But this new DSO role is effectively similar to the AEMO role that AEMO plays with the transmission networks. And Australia, by contrast, for those who are interested, in terms of setting up the governance arrangements for these roles, is probably a fair bit behind places like the UK. But in terms of managing and integrating renewables at scale and volume, is probably one of the leading markets for doing that. So, but we're just sort of moving through the process now to define roles and responsibilities formally. So this is kind of the roadmap where we are. We're basically really starting to see the governance of DSO emerge officially through regulatory processes and consultations, and we're going to see effectively by 2030 all of the DNSPs will be fully fledged DSOs if they aren't already. But it's basically gone from being passive, not passive, but an asset owner, to becoming an active manager. Focusing on trials and creating more opportunities on the LV and HV networks, and then really formalising that and taking it forward in earnest. This slide here just really talks about, again, more detail around the different types of roles that the traditional DNSP played, and how that's moving from asset manager to more active manager. But essentially, they maintain their traditional roles and then have to facilitate these new opportunities, and do that on behalf of the system and customers, and integrate renewables, and eventually manage EVs and offer flexible connection agreements and a whole range of other new services that coordinate back in with AEMO to keep the system running on behalf of everyone. So this is, again, just a different view of some of the key building blocks. So what you're required to run a grid and operate it, you need visibility, you need to coordinate the resources, and this applies for whether it's AEMO or it's the DSOs, the DNSPs. One of the new things that's emerging is flexibility procurement, so basically contracting aggregated resources to deliver services on behalf of the local network through some form of tender process, essentially, and doing that through new portals that are emerging, and also relying on batteries and other flexible loads to manage network peaks and potentially defer the need to upgrade the network and create some efficiencies there, as well as managing the coordination back into AEMO and with the TNSPs, having all the data and systems to manage it all, and maintaining all the regulatory requirements. So that's just a bit of a sketch of what's needed for the DSO. Probably the ones that are probably, I guess, well, the areas that are probably the newest, probably on that top row, 1, 2, 3, and 4. 3 and 4 really emerging, particularly 3 in Australia. In places like the UK, really well progressed and mature markets there. And I think in some ways we're emulating what they've done, but on the flip side, 2, we're miles ahead in terms of the total number of resources, and we've had to integrate and coordinate them in real time and manage them as they're going in. And I think Australia's done a great job at that, and a lot of other markets looking to how we've done that. And as a result, we've actually got quite good levels of visibility on the LV networks, relatively high levels of smart meters in places like Victoria, but even elsewhere. And really using all that data to actively manage the network and make it more efficient, or to do that efficiently, and to use data and insight as much as possible. So there's a lot of technology that you need to kind of run a DSO. So you need to basically you need to have all the kind of elements that would sort of feature in AEMO system, but much more targeted at the distributed level. So you need obviously a physical level. You need to have comms, you need to have data integration, you need to have analytics, and you need to have, I guess, some sort of orchestration and dispatch arrangement. and this is just an area that I sort of quite enjoy, but just talks to it's easier to say, but in terms of building it at scale and within utilities, that there's a lot to it. And then, of course, all of these systems have to coordinate back in through AEMO and make sure all of these distributed resources can provide maximum benefit for the total system. So that's another simplified diagram of what it looks like. But at the moment, if you could kind of look at that model, it's sort of the way AEMO runs the wholesale market. There's a set of constraints. There's a dispatch engine. There's a registry of all the resources. There's settlement functions. There's reporting, and so that kind of, I won't say complexity, but that arrangement, I guess, is being extended down into the distribution networks as well, and being built as we go, really to facilitate these millions of devices that I showed earlier, and coordinate them in the total system. So, yeah, quite a fascinating area, I find, and just one to watch out for those who are either in the industry or interested in the industry. And it's a new actor in the system. So I'll keep going. So next topic is voltage and frequency stability, and these are really fundamental elements of a power system. So voltage, essentially, the power system is designed as a constant voltage system, variable current, but you need to maintain voltage levels within regulated limits, and frequency is a fundamental dynamic for how grids operate. And a good analogy, it's like the heartbeat of the total system, and that heartbeat synchronizes and coordinates all the resources that are connected to the system. And as you move to something that's much more distributed and much more dynamic, you need to have the ability for parts of the network that come either are disconnected or experience some sort of interruption through a fault or a storm. They need to be able to be restored and synchronized to the effectively the grid's heartbeat, or even a local heartbeat. And to do that, it's quite a complicated thing to do in practice, but to do that without compromising the overall power system stability. So inertia, what we used to have was inertia and system strength, which came from the legacy plant. As I said, you had rotating mass that could provide inertia and support the system, and basically help restore it and recover it in response to some sort of fault. And that came about through large rotating mass machines. And as a result, the old, well, not the old grid, but the traditional grid also had a certain level of system strength that made it relatively robust to changes that meant that it wasn't going to become unstable. Protection systems could understand and see faults and identify them and isolate them and recover the system following faults. When you have weaker systems, that becomes more challenging, and so the potential for cascading, I guess, failures and dynamic instabilities increases. So they're just some of the key challenges that the grid in Australia and around the world is dealing with. But some of the new developments coming to the fore are what's called grid forming resources, so batteries and inverters. Basically, the inverters are the ones that connect to the grid, whether it's a data center or a battery, and they have the ability to dynamically manage a lot of these issues and provide some of the services that were previously provided by the legacy plant. So we've got really strong focus on all of these emerging topics from AEMO. Starting to see a lot of BESS come to the fore with grid forming capability. So that means that basically, in response to a battery being disconnected or sectionalized, it can restore and can effectively synchronize back into the grid with its own sort of heartbeat synchronization, and do that almost in real time and automatically. So that's important, and there's a lot of focus that AEMO's done on that. There's a lot of good work and reports they've done through different reports of the engineering roadmaps. Huge body of knowledge that AEMO and the sector is contributing to how to manage these grid forming resources, and eventually they're going to become the dominant type of resource on the system. And you can see there just got huge numbers already coming through that are providing these support services that you need to manage the grid. So it's an important area, and all driven by power electronics and how those systems operate. And as I said at the start, something that the rest of the world is definitely looking and paying close attention to how we're doing it here in Australia, because it's kind of proving that you can transition to renewables backed by batteries to firm the renewables, and do that relatively quickly, and still maintain all the things you need for power system security, reliability, and so on. All right, so the other dynamic as we replace a lot of the legacy plant is firming the grid, and I'll sort of really touch on how we're doing that, and that's mainly through renewables, but firmed by battery energy storage as well. So, rule of thumb, when you decommission a gigawatt of fossil fuel plant, you need to replace it by 3 gigawatts of renewables, and that's just purely because renewables have a lower capacity factor, so which is basically how often they run across the day or across the year, and obviously for renewables it's driven by weather, whereas legacy plant had almost infinite amounts of coal and gas available, so they could effectively run all the time or very high levels of availability. And so that's what we're seeing happen in the NEM. So based on the latest AEMO reports of recent months, we're basically putting, I think it's 4 gigawatts of new storage. That's doubled the total to 8 gigawatts. It needs to quadruple to over 32 based on AEMO's forecasts. And the batteries are really starting to play a role in the market. You're starting to see, the arbitrage spreads soften, but they're still significant across the day. And also, batteries providing significant amounts of what's called frequency control ancillary services, which are the raise and lower services that help maintain overall system frequency. And because batteries can respond so rapidly, they're really dominating those markets, particularly the fast ones. And when they first came in over 10 years ago, there was good sort of premiums from batteries providing FCAS, whereas now, because it's a really strong and well-supplied market, the total revenues for a battery from FCAS are now sort of drifting back down to historic levels, which is around 1% of the total revenue. So basically, we're using BESS to firm the renewables, and the way that's happening is through a series of sort of government auctions, whether through the federal government or the state government. So the capacity investment scheme is being run by the federal government. State governments have run their own renewable auctions. So in Victoria, we've had VRET 1 and 2, or VRET programs, and another prominent one in New South Wales at what's called the LTESs, the Long-Term Energy Services Agreements. So they're auctions for capacity that are going to either new renewables or BESS projects, and they're being done to facilitate replacement of the legacy plant and make sure that as we see the legacy plant retire or forecast to retire, that there's a pipeline of new generation and battery storage to back it up. And that's happening in the WEM as well, the West Australian market, as well as the NEM. So, the work I'm doing, BESS is pretty hot, very strong market here, and probably one of the hottest around the world at the moment in terms of BESS. And, the auctions are typically oversubscribed and, continue to run, and lots of announcements around new projects that are coming out all the time from those processes. This is just from AEMO's quarterly report from Q1 this year. It just kind of shows what I mentioned earlier, that the bottom left-hand chart there, the spread from intraday prices is falling, but still significant, and the contribution that FCAS is making for battery projects is really falling from what it was. So you can see in the top right hand corner there, the chart show that the green bars falling over time, and that just reflects the fact that really large amounts of battery capacity are available to bid into those markets and really having a dramatic effect. And it's interesting because when I started my career, I worked in that space. Of course, there were no batteries, but FCAS was typically 1% of total revenue, so it's sort of trending back to that historic number as well for batteries. Yeah, so with storage, the interesting thing is what you're seeing with batteries, it's really being dominated by lithium-ion 2 to 4 hour battery storage technology. So LFP is the dominant chemistry, and so that gives you, I think, the dominant lithium-ion range now is 4 hour duration. So if you have a 1 megawatt battery, it can provide 4 megawatt hours of storage, which is 4 hours of output. But of course, you need longer duration storage to manage the daily across the week and across the seasons. And we're starting to see some of these longer duration energy storage technologies come to the fore. So I've got two shown there, the vanadium flow batteries, the Energy Dome, which is a new one that's recently been announced, and as well as the, I guess, Snowy 2.0 or pumped hydro, which is a much bigger category of storage in terms of duration that's going to play a role to manage weather variability, interseasonal periods of weather variability, and support the overall system in order to firm the renewables that are going in and replacing the legacy plant as well. So it's fascinating, and as I said, Australia is really one of the hotspots around the world for this type of technology. And we're seeing storage go in small, medium, and large, but the large scale, you're really starting to see, particularly relatively recently, a lot of new technologies coming to the fore and new types of storage opportunities and longer duration emerging. When maybe even 2 years ago it was really just 2 hour lithium ion, moved to 4 hour, and now you're starting to see some longer duration technologies as well as pumped hydro coming to the fore. So I was given the guidance of talking for 40 minutes and giving 20 minutes of time for discussion. So yeah, maybe I'll stop there because it's got 20 minutes to go, and happy to open up to questions. I'm just sort of looking at the chat now, but
Well, thanks, Greg. That's good. You've done well. You've finished pretty much spot on time. That's good. So we will open it to questions, and I'll ask you to type your questions into the chat. And I see we do have one there from Glenn. Hold on, we'll just stick with Glenn's in a minute. I assume okay to put questions here. That's right. The Home BESS program is going well on numbers, but at a cost. Recently, Ausgrid has said would do DNSP CR for $25 per kilowatt hour subsidy and less than 5% capex into the RAB. And Essential Energy has even gone one better, and with Project Bolster says it will install 500 megawatt hours of DNSP BESS with no subsidy and on $0 on the RAB. Do you have any comments on this?
Well, yeah, thanks, Glenn. So one of the opportunities that BESS provides is the ability to value stack. So it can operate in the wholesale market as well as providing localized network support, and you can effectively use parts of the battery or all of the battery at different times for different value streams. So, for example, you could trade the battery most of the time in the market, as well as relying on it depending on the location and the network configuration for a very short amount of time to provide peak demand management, say for a coastal community or a seasonal peak. And so in terms of the economics and how the projects get structured, there's a process to facilitate networks to only allocate the element of the value stack that applies to supporting a network need onto the regulated asset base. But of course, as battery prices fall, and if there's value beyond just the, oh, sorry, if there's enough value there, then essentially you could have the scenario where the networks can deploy the batteries and not have to allocate much or if little to the regulated asset base. And the significance of that is that when networks invest to manage the network, then that cost gets socialized across the customer base. And one of the other things I probably should have mentioned in the presentation was that basically, the way the sort of energy system was structured historically, when it was, when the NEM came into effect about 20 odd years ago, a little bit more actually, was that you had transmission, distribution, retail, and generation all segmented, and that the thinking was that you'd segment the competitive and the monopoly parts of the value chain. And I guess networks were seen as the monopolistic part, but once you start seeing networks deploying batteries, well, there's a real change to that model where effectively the battery, if it's owned by a network, can be doing competitive things as well as regulated things. And so there's a whole series of rules around how that gets managed. So I personally think there's a great role for distributed storage. And I guess like anything, it doesn't matter who does it. If you can do that at scale and you can achieve synergies through a scaled rollout, then that's going to be beneficial for whoever the owner is or the operator. And I guess the New South Wales DNSPs are trying to demonstrate that in earnest, and they're doing some trials and recently came together to do a report called the DSP, the Distribution System Plan, to really show the benefits of unlocking renewables at a distribution level to support the overall energy transition rather than just focusing on doing it at a transmission level. So I think there's merit in it. I think if battery prices continue to fall, then there's the potential for them to become economic against network augmentation projects for networks. And with scale and volume, we can expect to see the prices falling. That they've fallen significantly, but they're still expensive and complicated to run, and there's a whole range of things that networks need to consider in that. But I think there's definitely merit in looking at that, and I'm certainly following what's happening in New South Wales with interest because I think that they're doing some good work.
So, Greg, we've got a question from John there, but I'm going to sneak one in if you don't
mind.
Sorry.
Just Chris, before we get to that, I don't know, Glenn, if you want to respond to that, or hopefully that was okay. Can we do that, Chris, or can we do two-way flow on the call or not?
I got to find him to unmute him.
Oh, that's okay. That's right.
While I do that,
Glenn knows how to contact me, so maybe just do that offline.
Yeah. So my question was, your presentation has been very much on the east coast of Australia, obviously. What about Western Australia, and how? I mean, what can you say about the two different systems in terms of this transition?
Yeah, no, it's a great question, actually. Yeah, I probably am showing my bias. I live in Melbourne, so I'm sort of very much live in the NEM professionally as well as residentially. But at WA, it's sort of a bit of a cliche, but they're different. They've always been different, and they've always done things differently. But that difference has been powerful. And in things like the DSO, that they were able to run a program called Project Symphony several years ago, which was really leading the way around showing how the orchestration can be done at scale. And it's really been quite influential in thinking about how that will emerge, across Australia. And one of the I guess benefits over there is that you've got effectively vertical integration and common ownership, which maybe it creates challenges, maybe it creates opportunities. But over on the East Coast, it's all mixed ownership, either public or private, and disaggregated across networks, generation, and retail. Some common ownership, but much more disaggregated. However, WA also, just when you look at it on the map, it's such a massive geographic area, have always had a distributed power system. So they've had the Southwest Interconnected System, which supplies Perth. Then they've had, significant, almost standalone, well, not standalone, but significant sort of privately owned networks that support the Pilbara and the mining communities. And then because of their vast geographies and sparsely populated areas, they've sort of become leaders in what's called standalone power systems, where effectively instead of having the network run out and supply several homes or properties, you can actually effectively have diesel or batteries and storage and some network for redundancy that can effectively give the same outcome. And they're really kind of forging ahead on that. So I think it's fair to say the East Coast has definitely looked at and benefited from what the work that's been done in WA. And similarly to auctions that are being run on the East Coast, there've been auctions run for WA exclusively, and similar outcomes where they're either contracting or underwriting new renewable projects or new BESS projects or both. Even though the numbers are smaller, but nevertheless the kind of trend is the same. Yeah, so good question, Chris. Are you from WA yourself, eh?
Just before we go on to perhaps Ian's question next, but what about to me, there's a lot of bureaucracy that's been added to the system, over the last couple of decades on the East Coast. Does WA have all of that bureaucracy too and all those systems?
They have the equivalents, yeah. So they have, well, AEMO now runs the market and system over there. They have a equivalent to economic regulator. Obviously, they have their own state government. The state governments sort of have the, I guess, the ultimate say in energy typically, but obviously are coordinated by the federal government. So all of that is the same. I think the difference is, and maybe it's an advantage, maybe it's a disadvantage at times, is common ownership and vertical integration. So whereas on the NEM, it was all disaggregated, over there it was commonly held.
Yeah.
And even though corporately they're different, I don't know, when you've got the same shareholder being the government, maybe there are benefits in terms of policy objectives that can be realised that may be harder to do on the East Coast. So yes, the short answer is they've got the same. They've got WA equivalents. And up until now, physically they've remained disconnected because of the distances.
Terrific. Great. Thanks for that. We'll jump to Ian's question, I think. Batteries are only good if you have something to charge them. Long and short-term fuel mix data indicates 60% of generation comes from black-brown coal and about 25% from renewables. With offshore wind stalling in Victoria and the imminent closure of Yalong W power station, what is going to change to give us cheaper, reliable power?
Yeah, so I mean, you're right. I mean, the batteries, yeah, I mean, and it's a bit like the networks. I mean, the networks follow the generation, right? So they're almost the primary thing you need in a power system is generation and load, and the load is obviously comes from us and our businesses and our economy. And then, of course, in order to use batteries, yes, you need to charge them and discharge them. And typically that they're being charged by excess not rooftop, but excess solar energy during the day. But they can also be charged from the grid, and where it makes sense to arbitrage that at different rates, that's what they're doing. In terms of the long-term forecast, yeah, it's really interesting. So even though we are decommissioning a lot of legacy plant, we are still heavily reliant on coal. And when you look out to say 2050, to get to net zero, there's a huge amount of new capacity that's needed. You've seen all the debates in the media about the nature of the generation. I mean, I've always personally felt that you need a mix, and we've always had a mix, and we're probably always going to have a mix. And even when you consider the targets, net zero, it's not a gross zero, it's actually net zero. So it implies that there are always going to be some underlying emissions, just that they'll be offset. So for example, if electricity can create can offset emissions in other sectors, and that's a good thing. And when you look around the country, I mean, it's a very political topic, but there are different sort of forecast technologies that are coming to the fore. So in Victoria, there's a program for offshore wind development to replace things like your lawn when it switches off, as well as onshore renewables. There's discussion about extending the life of the coal plants in Queensland and New South Wales. So I guess we'll continue to debate what is the optimum generation mix. It's very political and very dependent on government policy settings. Irrespective of who owns the assets in the end. So I think that will continue, and one of the new dynamics that's really come to the fore is data centers, and data centers are quite significant loads, can be up to a gigawatt for the hyperscalers, and that they're going to need a lot of energy. There's a lot of talk about them needing to bring their own energy, and it needs to be renewable. But the benefit that the loads bring is that can underwrite new production. And my personal view remains that we need a mix of everything, and that's why when you look at storage, you've got short-term residential battery, you've got pumped hydro, you've got transmission connected and distribution connected, sort of. So you've got a range of sort of scales and volumes. And physically, you need to have a range of technologies to match the different load profiles, whether it's the peak, whether it's the winter, whether it's different things, winter, interseasonal. And I think we'll continue to see that. But definitely the trend towards more renewables and lower emissions is sort of likely to continue, I'd say, because we've got national and state-based targets that in many cases, particularly at the state level, are bipartisan.
So, just carrying on from that question, Greg, if you look around the world, who's doing it better and what lessons can we learn from them?
Oh, gee, that's a hard one. I think Australia, in terms of, like, every market is unique, right? So Australia has a really long stringy networks, sparsely populated, right? So we've got different challenges to say in the UK, whereas the UK is much smaller, much more mesh network, much more densely populated. Our challenges are managing heat, peak demand, whereas theirs is managing winter, coldness, and transitioning off gas. So I guess every market's different. Who's doing it best? It's hard to say. I think every market's got its own challenges. I think everyone's doing something well. I think, for example, the UK is well ahead in terms of DSO governance arrangements than Australia is, but we're probably at the leading edge for integrating DER, even ahead of like some of the Asian countries. I know, some of the Southeast Asian countries are looking at Australia to look at how our institutional arrangements operate. And if you compare the US, they have in many cases either very small municipal type owned utilities to mega vertically owned SEC type entities, or mega vertically integrated utilities that are really big and can do lots of different things. So I think everyone's muddling through, and I mean that's so I can't really nominate who is doing it best. I think Australia's kind of where it needs to be, and it just feels a bit like we're all managing it in real time, which we are, to be honest.
So, just to follow on and drawing on the analogy of Telstra recently, how vulnerable are we to an absolute blackout or a stuff up like Telstra had?
Well, I mean, I think we're more vulnerable in the sense that we rely on the electricity system more than ever before.
Yep.
So I think, but in terms of its complexity, I don't think that has changed really. I mean, I remember doing reports as a young engineer on blackouts in far north Queensland that were driven by voltage collapse, and there were barely any renewables in the system. So the grid is always susceptible when it's above ground and subject to freak events or acts of God or earthquakes or bushfires. Like, it's always going to be susceptible, particularly in Australia. To bushfires is probably one of the most difficult things to manage in terms of the grid. I guess the consequence of failure is probably greater now because of the, diminishing role for gas for certainly domestic use. And one of the things that I see, and no one really kind of knows how all of these millions of devices are really going to operate together. So all of the kind of tools and frameworks are being updated in real time to manage that. So even when you look at how AEMA manages the system, they've got to adapt everything, that's been running really for 100 years since Edison and Tesla set it all up, to over the next 20 years, adapting everything for a distributed way of operating. I think things like grid forming inverters are going to provide more redundancy, and I think there's been a really big focus ever since the South Australian episode, the blackout there, to make the system more resilient. And I think the industry's done everything it can to manage the transition, but it's not without risk, but I guess the caveat is you can't ever defend a power system that's subject to the weather. It's above ground predominantly and covers really large
Yep.
distances. And one of the things I like about the distributed nature of where things are evolving to is that creates for customers some kind of resilience at the household or business level that maybe wasn't there before. So, if you've got a battery, you might have some backup. You've got an EV. If you've got a diesel generator, you've got some more backup than just relying on the network if it goes down.
Good. And we might have, thanks for that, but we might have time to squeeze one more quick question in. Kelvin has asked, is work done on the shape of the voltage frequency to keep it a pure sine wave to help industry electricity usage to be good for long life of their internal electricity-driven equipment?
Yeah. So one of the qualities of electricity, which it's not like a food or something you can touch or feel, is power quality, and so that relates to the shape and the how effectively perfect the waveforms are. And as was mentioned, there's a lot of equipment that's very sensitive to that, and if you get that wrong, the classic is flicker in the home. So if the power quality was poor, at a certain point you can start to detect the flicker, and it can cause health or just annoying impacts for humans. And obviously for really complicated, also really sensitive equipment, glass manufacturing is a good example. If you have these small variations in the quality of the power, then that can have an impact and compromise outcome. So the short answer is yes. And that's why everything is sort of tightly defined within certain engineering limits. And all of these new technologies have to be integrated and maintain those standards, or those standards need to evolve to reflect the new technology. So, yeah, good question.
Good answer too. Thank you very much, Greg. You've finished spot on time. We do appreciate the effort you've gone to prepare your presentation and deliver it. And I'm sure I speak on behalf of all of us attending this seminar, that we do greatly appreciate your effort and thank you very much.
Yeah,
Thank
thanks,
you.
Chris. And I just noticed there were some questions I maybe didn't get to, but yeah, feel free to ping me
Yep,
or directly, and I'll look forward to seeing you around the traps. Thanks,
terrific.
Chris.
And thanks to everybody who attended, and we look forward to our next seminar, and you'll get messages on that. Thanks again, everybody, and enjoy the rest of your day. Cheerio.
Thank you.